All right, let's go ahead and get started. So today we're going to talk about proximal Newton methods. And this essentially is we talked about proximal gradient methods already in the class, right? So which was a way of kind of optimizing non-smooth functions, at least simple non-smooth functions, with a thing that looked like gradient descent, but had this extra prox operator involved, and ended up inheriting a lot of the nice properties of gradient descent, like linear convergence and stuff, despite the fact that it had this non-smooth term, even though you could also despite that it has non-smooth term, as long as you could solve this prox operator. And today we're going to talk about the Newton version. The natural question for that is, well, is there a second order equivalent of this? And there is, and it's called the proximal Newton method, but it does have some caveats, and we'll get into all that in a little bit. Before we start, though, I just want to give a brief recap of last time. That was quasi-Newton methods. And these actually will come up again this time, very, very briefly, just in terms of proximal quasi-Newton methods. So everything we're talking about today in the Newton case, in the proximal Newton case, can also be extended to the quasi-Newton case. So you can develop, you can have that similar kind of superlinear convergence without the n squared cost for proximal Newton methods as well. Though again, there is this caveat that I'll get to about quasi-Newton methods in a second. But remember, quasi-Newton methods were about optimizing a unconstrained twice differentiable function. And the idea here was that although we didn't want to do the full Newton method with the actual inverse of the Hessian, we formed some approximate Hessian, or really approximate inverse of the Hessian, that we called either B for the approximate Hessian, or B or C for the approximate inverse of the Hessian. And we would do our updates like this. And the key part about the different quasi-Newton algorithms was how they actually performed the update of this, or computed and performed the update of this B or C matrix. So for example, SR1 did a rank 1 update for the Hessian. BFGS, which actually introduced first, did a rank 2 update of the Hessian. DFP is a rank 2 update of the inverse Hessian. And then LBFGS was a limited memory version of BFGS. So today, though, we're going to talk about proximal Newton methods. And first of all, are there any questions from last time? I can actually ask that because I taught it last time too. OK. So today we're going to talk about proximal Newton methods. And at a very high level here, I kind of want to sketch out sort of the landscape we've been talking about optimization as a whole. So in terms of the methods, there's first order methods here and second order methods. So this is gradient descent on second order. So this is canonically Newton's method. Oh my goodness, this is zoomed in way too much. There we go. I don't know why it zooms in at all. I don't know why you'd want it zoomed in. Second order methods. And so for sort of, unconstrained smooth functions here, this is just gradient descent, right? We just have normal gradient descent. For our first order optimization method for unconstrained smooth optimization. And that gets linear convergence. That's nice. Our sort of canonical second order method here was Newton's method. And then kind of in between here, we had quasi-Newton methods, right? Quasi-Newton. All right. To draw this sort of matrix here. So then, on the other hand, if our function class was non-smooth or constrained, but kind of simple, and by simple I mean here has an efficient prox operator or an efficient projection operator equivalently, because the prox is a generalization of the projection. So this is going to be non-smooth. I'll just sort of call it like non-smooth simple here, i.e. with a prox. Then we have proximal gradient. Right. And sort of the last, and then we don't really know what this thing is here. We'll talk about this here today. And then sort of non-smooth I guess I'll just call it complex here, not like imaginary complex, just like hard, general. I should probably call it like general. Though again, general is in quotes because you still have to phrase it in terms of like a Cohen program or something like that to really solve these things. Here we have interior point methods, right? They can solve, with a second order method, they solve general constrained problems. In the first order category, we kind of have, I guess you could say we have like subgradient descent, so subgradient descent you can technically apply here. But with a big caveat that it doesn't actually convert, not fast convergence. In other words, you'll get or you get sublinear convergence, so you don't expect to really get an accurate solution to numerical precision. And then today we're going to kind of talk about, and then I guess here there's some stuff too, but I don't know if we get to those in this class. And then today we're going to talk about kind of this region here. So what can you do with the second order method if you have a non-smooth but kind of simple function, right? So like maybe an L1 penalty on some general loss that you want to optimize, but you want to be able to do it kind of exploiting maybe the structure of that, something like the prox operator. Okay, so this is the topic of today. Any questions on that? Is this in focus, by the way? I feel like the focus is not quite right here. That's brightness. That's not what I want. Well, might have to just be life. Okay. Autofocus, is that right? Autofocusing. There, that's better. Okay. So this is sort of the outline of the problems we can solve, and this is what we're going to talk about today. So let's first recap proximal gradient descent. And the idea here is that we want to solve some problem minimizing g of x plus hx, where g is assumed to be convex and smooth. So it's a general kind of convex function, but a smooth one. But h is convex and it's not necessarily smooth, but it's kind of simple. So one of the common examples that's brought up is the L1 norm. So that's not a smooth function, but it's simple in a way. And the update here is very simple. We just repeatedly solve the update. Xk is equal to the prox, and he says sort of prox t here, which is some step size, where the step size manifests here in the prox operator. He says prox t, xk plus 1 equals the prox of xk minus t times the tk times the gradient of the g of xk. I guess he wrote it there with indices. xk, I wrote with xk plus 1, but same thing. So we just repeat this update, and this is kind of like a gradient update we saw, but it involves this additional prox operator, right? If it was just this thing, it would be a normal gradient update, but we had this additional prox operator there. And the prox operator solves another optimization problem. So it sounds like we're kind of, creating more work for ourselves. The prox operator of x is equal to the argmin over z of 1 over 2t x minus z. So you find the closest z to x while also minimizing some other function, this other non-smooth function h of z. And that's the prox operator. And the whole point of the prox operator in some sense is that this is very nice because our outer iteration here, our sort of main prox step, it inherits all the nice properties like linear convergence and such of gradient descent. But of course, being able to implement it efficiently requires that we solve this problem. So it's only really applicable in the cases where this problem is solvable in a nice closed form. And so there are some examples of this, though, like, for instance, if h is the L1 norm, you can actually solve this as a very simple analytical form in terms of soft thresholding the values in x. Right? So if you can do it, this is a very nice thing because it allows you to incorporate these constraints that, if you solved it with subgradient descent, the original problem, you wouldn't get nearly as fast convergence. But it's sort of, it lets you get the nice properties of gradient descent as long as you're able to solve this prox operator well. So that's nice. The other thing that we want to sort of point out here, I'll just sort of say this, is that if you just expand these definitions here, what you see is that the proximal gradient descent is sort of doing something like iteratively minimizing a quadratic approximation of the function, in this case g, plus the original h, where you assume though, so it's sort of like minimizing, I guess he says x plus is the argmin of something like a quadratic approximation of around of g here. So it's the gradient of g x transpose z minus x plus, I'll just write it like this actually, 1 over 2t x minus z squared plus h of z. So it's something like a quadratic approximation. You can think of this term as like a quadratic approximation to g, but essentially with the Hessian approximation being equal to basically 1 over 2t times the identity, which is, just 1 over t times the identity. The 2 is always the factor there in quadratic terms. So it seems like a reasonable approximation, but it isn't a good approximation because we're using just the identity as the approximation to our Hessian, which is not necessarily going to be very good. Whereas Newton's method, when you think of it in the same way, it would minimize the quadratic approximation here with the true Hessian in place of this identity. So the question, of course, sort of is, what happens if we replace this 1 over t times I with the actual Hessian and try to apply a proximal operator, a proximal method? So what this is going to lead us to is the proximal Newton method. So I'm going to write it like this. So first of all, I'm actually going to write this a little differently. I'm going to write this. Just notice this operator here is equivalent to the argmin over v. V here is really z minus x of, actually, which way did he have it in the previous one? Did he have, yeah, okay. The gradient with respect to x of g of x transpose v plus 1 over 2t norm of v squared plus h x plus v. So v is like our additional term here. So I'm just going to note that you can write it like this to the original proximal gradient descent. And we're going to write the Newton version in the same way. So this is sort of, proximal gradient. What we're going to do is we're just going to write the same thing, but replacing this term here with the actual Hessian. So we instead would like to have the update. I'll just write it in terms of sort of our update. So v, let's see, I guess vk equals the argmin over v, gradient to x. I'll omit the subscript. No, I'll just write it the way he does it in the slides, actually. The gradient this times transpose v plus, instead of this term, we're just going to place the actual Hessian there. So v transpose h k minus 1 v, and then plus h x k minus 1 plus v. Okay, and then we're actually going to update x to be xk minus 1 plus some step size t times vk. Okay, so we're just doing the same thing with proximal gradient here. Just doing it in this, just replacing the identity here with the Hessian. Right? So the question is sort of, what does this do? What is this method here? I should just mention you can also sort of write lots of different ways. You can also write this in terms of in sort of the the zk form. So you can write it in this form or in this form. And he just has both of those now on the slide. So it's either this form or this form. But both these two things work. Okay. So this here, I guess I'll just do it like this. So these two things, let me just be clear. This is proximal gradient. And this is proximal Newton. Where here, h k minus 1 is just equal to the Hessian, importantly, of the smooth component of our function we're minimizing. So just the Hessian of g. I guess I evaluated it xk minus 1. There we go. Get all those superscripts in the correct place. So the question is, what does this actually do? How does this work? And sort of, is it a practical algorithm or not? And the answer actually is a little bit tricky here. Because it does work. And so if you're able to do this, as you would expect, you get all the nice properties of Newton's method. So you get quadratic convergence, all those kind of things. Even though you have a non-smooth part of your function. So that's great. But unlike the proximal gradient case, solving this problem here, this argmin, can be actually quite hard in a lot of cases. It doesn't have a simple form like you often find for the prox gradient term. And so actually solving this can be rather difficult. So this method, as a whole, can be actually very efficient. It can be state of the art for a lot of problems. But that requires a special method for solving this inner argmin here. And if you have that, then you can do well. But it's not nearly as often as it is in, say, prox gradient that you have this method. All right. So again, just some notation here. This term here is called the scaled proximal map. So whereas the proximal map was just the function, essentially with the identity here, scaling it, we can define also a scaled proximal map that basically has instead of going from prox t of x. So I'm going to write it again just to have them both. Prox t of x being the argmin over z of 1 over 2t x minus z squared plus h of z. Prox h of x, which is a strict generalization of this, is equal to the argmin over z of 1/2 x minus z in the h norm squared plus h of z, where the h norm of a vector x is just equal to x, just defined as being x transpose hx. So it's just the quadratic form with that inner matrix. And this is called the scale proximal map. And of course, if we just plug in 1 over t times I, we get back the original proximal operator. But this will be how we do it. Note there's a little bit difference in terms of you usually define this thing with a 1 over t term here, where this just has the h term there, but that's just notation. And so of course, our prox update, which we have here, our prox Newton update, can also be written in terms of the proximal map, right? Because our z here, which is the minimum of this quadratic term plus that other term, can also be written as in terms of the h norm of this thing. So in other words, I think that's the next slide. The prox Newton method can also be written as zk being equal to the scaled prox map for the k minus 1 value of the Hessian of x k minus 1 minus this term hk minus 1 inverse times the gradient g of x k minus 1. And then we do our update as before. Then xk equals xk minus 1 plus tk of our previous thing of zk minus x. Okay, so we can also write our prox Newton this way. in terms of the scaled proximal map. And the high level here really, at some level, is just kind of saying the obvious thing that we can also define this generalization of a prox operator, that instead of having a normal L2 norm squared as the thing we're sort of measuring closeness by, we just measure closeness by this other quadratic form. That's really all it's saying. All right, any questions? And a few quick points. Of course, the difficulty of running that prox method depends strongly on whether or not we can solve this prox operator, which often depends in the course very strongly on how complex that Hessian is. So if the Hessian is diagonal, for example, then you can actually solve it very efficiently, the same as a normal prox operator. But if the Hessian is dense or something like this, it can become a lot harder. And so we'll talk a little bit about that, though actually we're not going to cover the way these things are really solved in practice. So the way they're often solved in practice actually was based upon a subsequent lecture. I'll mention it and I'll call it out here, but we won't actually talk about how to solve the inner prox operator, because in many cases actually is not that easy to solve. Any questions so far? Okay. Well, that's a good thing or a bad thing, but we'll keep marching on. Okay. This is a little more little kind of details here, but just like proximal gradient, to get all the nice convergence properties, you do need a line search method as well with proximal Newton methods. And it uses mainly the same kind of ideas of backtracking line search that you use for normal gradient descent or for Newton's method or any other sort of thing, but with a little bit of a twist. So we know from, or I'm telling you at least, you don't know yet, but I'm telling you that prox operator is sort of very expensive to compute, and you don't want to compute it a lot. Well, in normal backtracking line search, say for prox gradient, we repeatedly evaluate the prox operator in the steps of the backtracking line search because it's relatively cheap in those cases, and you can get get convergence that way. But the only thing I want to emphasize here is, and the formula is here, but what's actually important here is that the way you typically do backtracking line search for prox Newton is that you do it in a way that does not require you to solve the prox operator at each backtracking step. So instead of that, we actually define this delta here, which is the prox operators. That would be the update with a full step minus x. Of course, that's the updates we make. That's the update we would actually make to x. Then we introduce some step size t, and we repeat this until we repeatedly scale t by beta here until this condition is satisfied, that x plus our update. The function value of x plus our update, remember f includes both g and h, so the total function value of our update is greater than, until you repeat it until this is less than this plus our sort of first order approximation plus some scaling of the prox term as well. And really the only important thing here is that, or the main important thing here, is that this backtracking line search does not actually involve the prox operator. So we don't actually run the proximal step in our backtracking line search. All we do is we just sort of have a slightly different spirit of method that requires that we just evaluate the function again and again at the different stages of our backtracking, not its actual prox map. So the details are there, but if you want to implement it, just use that formula. But that's the basic idea. And so we try to not spend too much time in backtracking, or at least rather, we don't want to spend too much time in backtracking, so we eliminate sort of the most complex part of the algorithm when we're backtracking. Okay, so let's sort of summarize now a little bit. So proximal gradient iteratively minimizes this sort of just normal squared L2 norm plus the non-smooth portion. It often has a closed form for that iteration. That makes it fairly cheap, and it gets the convergence properties of gradient descent. Proximal Newton, on the other hand, iteratively minimizes some other quadratic form plus this non-smooth term. There's almost never a closed form to that prox update, so actually doing that is quite complicated. And the iterations are very expensive. But if you can do it, you get the convergence of Newton's method, so you get quadratic convergence. actually, does he? Okay, let me actually, before going on, let me actually say sort of how this is done in practice. So we aren't going to cover it, but the cases where proximal Newton works well, the things that I've typically seen are when you can solve this inner problem relatively efficiently, even though you can't solve it in closed form. So for example, that problem, what that is, take the example of the L1 norm. That's minimizing a general quadratic with an L1 norm additional penalty. That's not an easy thing to solve, but we do have some pretty fast methods for solving it. And in fact, one of the fastest ones is methods like coordinate descent, which I'll cover later in this course. So what people actually do is there are classes of sort of sets of functions where minimizing that problem using coordinate descent at every iteration of a Prox-Newton method is actually better than running coordinate descent on the original method itself. And that's because coordinate descent on a quadratic form has a specific kind of update you can make that makes it very efficient without having to constantly reevaluate the actual gradient and the Hessian itself. That's actually all I'm going to say for now, because you will cover coordinate descent later, and there's some later slides on doing that. But essentially, even though there is not a closed form, the high level here is there are classes of problems where it's easy to minimize that, relatively speaking, and you end up getting an algorithm that performs better than if you just try to directly minimize your original function. So take that for what it's worth, but we're leaving it a little bit unsaid right now because we haven't covered coordinate descent yet, but that ends up being the thing that's used most often for the inner prox step. Okay, any questions on any of that? There's got to be some questions. Yeah.
But again, why we don't need to reevaluate the prox operator in backtracking search?
Why we don't need to, or the fact that this doesn't do it? So sorry, how this doesn't do it, or okay. Well, so I mean, at a high level, this just doesn't do it, right? So there's no prox in the backtracking line search here, right? So what you're doing is you're forming, I mean, what's sort of going on is that you're kind of forming an approximation to the function that involves kind of these, remember when Ryan talked about the generalized gradient, which is kind of this function that's kind of like the prox operator? You're kind of doing backtracking line search on the original, on the composite function, plus this sort of generalized gradient-like term is kind of what you're doing. And the difference here is that, I guess the difference between normal is that you have this alpha term that multiplies both your next step and your current one for just the h term here. And that allows you, that basically is the generalization that allows you to not have to recheck your sort of prox operator each time. You just check the actual values of the function themselves and see if the function itself is sufficiently decreased. And it kind of works. I mean, I guess this is kind of hand wavy, but it kind of works because it's using things kind of like the generalized gradient in the backtracking line search. Yeah. Oh, I'm sorry. So, okay, maybe this isn't very clear. So the question was, do we still need to use the prox to get v? Yes, you do. I mean, just to be clear, you have to evaluate the prox to do this. The point is, the way backtracking line search is that backtracking line search is it's like a while loop, right? It's while this condition is true, I multiply t times equals beta times t, and then I reevaluate this thing. The point is, if you look for the backtracking line search in the prox step, the actual evaluation here involved the prox operator, meaning that if we ended up doing 10 different backtracking steps, we had to evaluate the prox operator 10 times. Here we have to evaluate it once at the beginning of the iteration, and then in the actual backtracking procedure itself, we don't reevaluate it. We just evaluate that one time, and then that's good. All right? So that's a big difference. If the prox operator is expensive, then doing it once per backtracking step would be very, very costly, and so we avoid that with this particular line search instead of the normal prox gradient line search. Did that maybe clarify your point up there too? Okay. Yeah.
Would you use this for the regular prox
You can, I believe, you can do that, but actually it's no more efficient for the prox gradient, and I think the other one's a little bit more natural for the prox gradient. Yeah. I mean, assuming you have an order n, assuming basically computing your function value is the same complexity as computing your prox operator, which it is for most normal prox operators that we have. All right. So now let's talk a little bit about convergence of prox Newton. And I'm going to sort of, this is going to be a sketch relative to the convergence proof we had for Newton's method, but it really uses a lot of the same properties. And I'll kind of try to highlight one in a little bit of detail, but we'll kind of go from there. So the first thing we're going to, the assumptions we're going to use here are similar to the Newton assumptions. Actually, it's also similar to the quasi-Newton assumptions, for the convergence analysis at least. We're going to assume that the Hessian of the smooth part of G is bounded below by everywhere by little m and bounded above everywhere by big L. And the Hessian itself is Lipschitz with parameter big M. And so, of course, I mean, again, these terms kind of act like strong convexity and Lipschitz continuity on the function itself, and then the other term is required because this term kind of bounds sort of how far from quadratic is our function. The Lipschitz constant on the Hessian says kind of how far are we from quadratic. If the function was quadratic, that Lipschitz parameter m would be 0. And so you would have instant conversions like you do with Newton's method. We also are going to assume for now that we can exactly evaluate the prox. We'll get to kind of breaking that assumption a little bit because the reality is you can almost never exactly evaluate the prox. You almost always solve that one approximately. But assuming those two things, we have the following proof or following convergence proof for prox Newton. So what we have really, again, is quadratic convergence. So we have local, well, I should say, it converges globally, and locally, that is for some sufficiently large step, we get quadratic convergence, meaning that the difference between and I should say sort of local quadratic convergence, meaning that the difference between successive values and the optimum in 2 norm is actually equal to some constant, and the constant here is just actually big M over 2 little m, times the previous difference squared. So if this is small, this thing is small squared, so it just immediately goes to 0, basically, for all intents and purposes. And this means we need log 1 over epsilon iterations to achieve precision epsilon, which is like 6 is as big as you can possibly get that thing. So it's pretty fast. All right, so how does this work? So there are really, like normal Newton's method, there are really 3 steps, 3 sort of elements to this proof. The first 2 which I will just sort of mention but not show, and the last one, or say what they're saying, and the last one I'll go into a little bit of detail about it. So the first one, the first sort of property that holds, is that you can show that the backtracking line search will always terminate. It will never go on forever, and sort of, because that's sort of the danger here. The danger here is that this process with this line search will just go on forever, and if it goes on forever, or it gets really, really small, maybe vanishingly small each time, it gets smaller and smaller each time, then you obviously aren't going to converge, right? You can just take smaller and smaller steps and never actually reach an optimum. So what the first property shows is that this condition, in other words, the backtracking line search condition, will always be satisfied as long as t is less than the minimum of 1. Well, that's sort of obvious. It has to be at least 1. And 2m over L, L times 1 minus alpha, where alpha was one of the parameters of the backtracking line search. Okay? So as long as you have that condition, you will terminate your backtracking line search I mean, hopefully with a bigger t than this, but at the very worst case with this amount of t, that will decrease your function by some fixed amount. And so therefore you are eventually going to converge. It actually will give you linear convergence too, though I won't, that's just sort of a side effect because that's actually bounded by some constant. And so you will actually converge and your function will decrease by a certain amount. So that's what this first part shows is that you will converge you will eventually converge to the optimum of this problem. It will not run forever. And in fact, it will get linear convergence globally. The second property is that theoretically there is for large enough k, but for large enough, for large enough k, or equivalently for xk close enough to the optimum, because that's what happens with large enough k, you will actually, backtracking line search will exit with t equals 1. So you will take the full Newton step after a certain point. Right? And this is actually proved very, very similar to how you prove the same condition for Newton's method. It essentially just follows from the curvature of the function, this Lipschitz constant on the this Lipschitz constant on the Hessian, and you get this point. And the third one is that when you take a step of t equals 1, you have local quadratic, and k is big enough, you have local quadratic convergence. And this one I might spend a little time with. So you have the fact that my next iterate is the 2 norm of this is less than this constant times the 2 norm squared of the previous iterate. This one isn't too hard to show. It's going to use the non-expansiveness of the Prox operator in the H norm, plus some other properties. But basically, it goes something like this, I think. So if you have x plus minus x star, the 2 norm of this is first of all just going to be less than or equal to 1 over the root m times the H norm of this same thing. That just follows. That's just a simple property of H norms, right? Because this can only grow it basically, or this is going to be bound. This thing is going to be less than this thing, where this thing can only scale it down by 1 over root m, where m is the smallest eigenvalue of H. Next, you can expand these two things. So we also know this is less than or equal to 1 over root m of the prox of x minus h inverse gradient of g of x minus the prox of x star, because x star is a fixed point of the prox operator. I guess I'll write prox h here. Prox h minus the prox of this thing. So that's the prox step, at the optimal point, which we know is the same as the optimal point there. Norm h. Next, use the fact that the prox operator is what's called non-expansive in this H norm. I won't prove that, but I think that was shown for the normal prox operator before, I believe. So what that says is if I have, the prox H applied to something evaluated in the H norm, I can remove the prox terms here. So this is also less than or equal to 1 over root m times just this thing removing the prox operator. The prox will only sort of contract the difference in this H norm of x minus h inverse g of x minus x star plus h inverse g x squared in the H norm. And now I'm actually going to, how do this? Yeah, now I'm going to remove this h term. So I'm actually just going to bring this into the expression. So I would get like an h to the 1/2 there. And I'm going to add one more. This is a little, hopefully this makes sense here. What I'm going to do is I'm actually going to add an h inside here and get rid of it here. And that will add another 1 over root m term. So I get in total 1 over m times h of times this thing, which is h times x minus x star minus g x plus g x star in the 2 norm. Okay, that was a little tricky. What I did there was I basically first distributed this inside, then added another term like this, and then distributed that one inside. So I moved the h in front there, and this, of course, canceled against these things. And this is now actually, you can kind of look at this and see that this is actually this is actually like a Taylor expansion of the gradient of g evaluated at x star. So let's put a little bottle. So this thing actually is this is sort of the answer. This is now less than or equal to m over 2m of x minus x star. But to see why this is the case, you can sort of think about the gradient of x star. Actually, I'll just say the gradient of x. This is equal to the gradient of g at x. This is equal to the gradient of g at x star times the Hessian of g which is at x here, times x minus x star, which is exactly what we have inside here, plus some term that depends on, x minus x star squared, right? Because that's sort of our Taylor expansion. We have only terms that are sort of lower order than x minus x. They're x minus x squared. And if we actually want to bound this thing, so have the norm of this minus that, then actually this is this whole thing is less than or equal to the Lipschitz constant of this guy, which is m. And this, yeah, m times x, sorry, this is squared. M to x minus x star squared. So that's sort of how you prove this. The square here comes from the fact that this is a Taylor expansion of the gradient of x around x, and then you just bound it with the Lipschitz constant there. So that's sort of how this works. And again, the important part here is that you get, because the remainder terms are all of the order of x minus x star squared, you get this extra square term there. And that's what gives you quadratic convergence, assuming you take that step size of 1, which again, we know we take that step size of 1 eventually. Right? So I mean, this is, I think, just details. This isn't too important here, other than the concept of how you get it. This is you can prove the convergence of Newton's method in a very similar way. I think you did something very similar to prove Newton's method's convergence. And basically, you have the same kind of proof for Prox Newton as well. Does these steps all make sense here, roughly speaking? Yeah. 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 So let me sort of say this, okay, because that one's kind of weird. So what I did was I had some term like y in the so I had a term like 1 over square root of m of the norm of y in h, right? This is equal to 1 over root m of the h to the 1/2 times y in the 2 norm, which, using the same rule we applied above, is less than or equal to 1 over m times h 1/2 times y in the h norm, which is equal to 1 over m of h y in the 2 norm. So I was just like doing this thing twice, using the same minimum eigenvalue bound twice to also move from a square root here in the denominator to just to m in the denominator. Does that make sense? Sort of overlaying this again. So I had this here, I move the h to 1/2 times this thing. I apply this thing again to add another h there, and then I move that h inside. It's just basically done that way so that these h's cancel out and I get an h in front of x minus x star. Yeah. Yeah. So that's So how did I go from here to here? So this is a property of prox operators in general, which I actually won't prove. It's called the non-expansive property of prox operators. Did Ryan cover that for normal prox operators, non-expansivity at all? So basically, if you have, so the property is that if I have two points, x and y, so if I have x and y, then if I take the prox h of x minus the prox h of y in the h norm, this is less than or equal to just x minus y in the h norm. So when I apply the prox operator to two terms in inside a norm like that, it will only bring them closer together. This is often easiest to see actually kind of visually for like a projection. So if I have 2 points, like the projections are non-expansive, for example, right? So if I have 2 points, I'm say projecting them onto the set. If these 2 points are this far apart onto a convex set, then projecting them onto the set can only bring them closer together. It can never bring them farther apart. And the same intuition holds for prox operators, that taking the prox of taking the prox, including this prox Newton, or this sort of scaled prox, of 2 different vectors, that can only decrease the distance between them in the prox, in the same norm, H. And this is called just the non-expansiveness property of the prox operators. It can stay the same. I mean, of course, if they're already in, like if the 2 things are already inside the set, then it wouldn't change them at all. So it's less than or equal to that. But it can never bring them farther apart. Yeah?
So the first inequality on that page, that would only work for positive definiteness.
Oh yeah, that's a good point. All this is assuming H is positive definite. Yeah, so it's actually also to be clear, like this is assuming that not only is it positive definite, it's actually positive definite with minimum eigenvalue m. So all of this assumes that. So you definitely need that to prove any of this. If H is, if your Hessian is not positive definite, not only does this not go through, the method does not work, right? And this method does not work if you have an indefinite Hessian, or even a semi-definite, a Hessian with 0 eigenvalues. The inverse doesn't exist then, and so all bets are off. And in fact, for this proof, you actually need more than that. You really need this strong convexity, it's called, right? You need this minimum eigenvalue condition for this version of the proof. There are other versions, I think Ryan might have alluded to, called self-concordant Bayes analysis that relaxes that assumption and gives it an easier type or a different type of assumption instead. But here we're just assuming strong convexity. And so there you have strict positive definiteness of the Hessian. Yeah? It's in the 2 norm, I believe. Yeah. That's sort of how the Taylor expansion usually works, is measured in the 2 norm. Yeah?
Do we need to big N over too small and just less than 1?
No, it actually should be bigger than 1. It almost always will be bigger than 1, right? Because I guess, right, sorry, it doesn't actually, it's not the same as L and M, but no, it can be bigger than 1 by quite a bit. The point is, this can be big, but as long as this is small enough, this is like small squared is really small. It's going to overwhelm any constant here. So as long as this is, so it's sort of, it's okay if this is big. It's not like normal, like linear convergence where this has to be less than 1, otherwise it's vacuous. Here, this can be big, but as long as this is really small, this will still drop off. For small enough differences here, i.e. for big enough k, it'll fall off. Yeah. Okay, so that's great. All sounds good. So the only thing that I want to point out here is that this is a practical method, despite everything I've said so far about, well, you have to solve this prox, but I haven't told you how to do. There's no closed form like there is for the normal prox operator, for these scaled prox maps. In fact, they involve solving something which seems like a hard problem, like a general quadratic form plus an L1 constraint. That already seems like a pretty hard problem to solve. But it turns out for certain classes of problems, these really are some of the state of the art. So the most common, to be honest, the one that I see most are L1 regularized problems with a non-quadratic loss or a non-quadratic objective plus an L1 term for sufficient sparsity. So for very sparse solutions, this ends up being one of the state-of-the-art methods. Two of these methods are called GLMNet, so that uses prox Newton for general L1 penalized generalized linear models. The inner problems are solved using coordinate descent. Quick uses prox Newton for the graphical lasso problem. There actually is some fancy factorization tricks you have to do, so you have to sort of store and cache certain elements of the Hessian when you're doing your coordinate descent updates. But you can do that, and then again uses coordinate descent for the inner loop. Notice the pattern here is that all the state-of-the-art things use coordinate descent for the inner loop. It turns out for L1 regularized problems with quadratic terms, coordinate descent works incredibly well. And these are essentially exploiting that to make a fast outer algorithm when you don't have a quadratic term. So when you're minimizing some other function plus an L1 term. In which case, just to be clear, on the original problem, coordinate descent would not work very well because you have to recompute Hessians or gradients each time you want to make an update. So essentially, these methods for the right scales, i.e. for the proper amount of sparsity, are state-of-the-art, and they really can be the best methods of solving some of these problems. Just to give a few sort of hints at that, this is an example from Lasso, just logistic regression with an L1 regularization term. Showing here the FISTA algorithm, and I think SPARSA sparsa is a spectral projected gradient method, again, versus proximal Newton. So you need many fewer function evaluations, and it's also quite a bit faster than other methods, though this case actually isn't hugely so. There are some cases where everything else, including FISTA, is incredibly slow, and this thing just finds solution incredibly quickly, especially for low sparsity levels. The reason here why, by the way, you need, like this looks much better than this one, is that prox Newton spends a lot of time not just evaluating the function itself and the function's gradient, but actually computing the proximal map. So it uses many fewer function evaluations, but you don't get quite as big a win on time because still solving that proximal map takes some time. Even though it doesn't take many function evaluations, it still takes some time. And similar for different size problem. I actually think that this example before, so this Quick paper, I think has some of the most compelling examples I've seen of that. If you want to look up that paper, it has cases where essentially, you get a similar plot like this, but the proximal Newton is like a vertical line on the left here, where it just solves it instantly, and everything else takes hours or so. So for certain problems, this can be a really compelling method. Okay. So let me highlight a few additions now that we can talk about. And this I'm going to go kind of fast through this because I do want to have time for the last thing in this lecture, which is about projected Newton methods. So the first thing to say, and actually this would already speed up, make the graph in the last one look a lot better. The first thing to say is that with proximal Newton, we are almost always not going to actually solve that proximal map exactly. Unlike, again, proximal gradient, where there's a closed form expression, here we're solving it with some iterative method. And so it'd be really nice if we didn't have to solve it, to full precision every time. Especially in the early stages, you say, okay, if when we're just starting out, maybe we'll get a good initial step by just solving it, to some nominal accuracy, the inner prox operator. And then take that step, and then maybe only as we get really close to the solution do we solve it to higher precision. It turns out you can do this exactly. So here are some plots on an adaptive versus sort of an exact versus capping the maximum iterations at some number. And the important plots to show here are actually these two here. So the red line is exact. It means that you are solving, to numerical precision the prox operator, whereas the adaptive one actually solves it to a stopping rule I'll show in the next slide. So basically, at earlier iterations, it stops the inner solve of the prox map sooner. And the point here is that you essentially, if you pick the right rule, which is called this adaptive rule for determining when to stop your inner step of the prox solution, you basically get the exact same convergence in terms of the number of iterations as the exact method, but you require much less time than it. And in contrast, you have to be smart here, though, because if you just were to say, okay, I'm only going to run, say, 10 iterations of my inner prox solver, 10 coordinate descent iterations, something like that, you actually no longer get quadratic convergence anymore. You get it works okay, but you actually are slower than even the exact method, and you get it's no longer quadratically convergent. You can see you get linear convergence again. So you lose your nice properties of the approach. And all I'll say about this, I just want to highlight this briefly here. Remember, there was something similar said about Newton itself. So you could also sort of do the Newton solve only inexactly. And there was this condition that, we wanted to solve the Newton such that the norm of our approximate, that's our quadratic approximation, was less than some, constant times the norm of the true gradient, where the etas here go to 0 eventually. And proximal Newton does the same thing, but using these generalized gradients in place of the true gradient. So generalized gradient, remember, was defined by the normal prox operator, not the Newton prox operator, just defined by the normal prox operator. And then they just use that and said, there's some complicated rule for how you pick etas here, but we're not going to worry about that. It's just basically, as long as you ensure that you run to some given accuracy, you are guaranteed to actually, in this case, achieve a superlinear rate if you follow this pattern. So similar actually to the quasi-Newton methods that don't get quadratic performance, they get superlinear performance. If you follow this precise sort of method for picking how exactly you want to solve the prox map, you get similar superlinear conversions. And this is sort of what it looks like. It looks essentially exactly the same, and takes much less time. Okay. The last thing I'll say about, until I get to the true last thing, second last thing I'll say, is that, of course, so back to my original sort of slide here. Where did I want to keep these in the right order. Here we go. So back to my original slide here. So far we've been talking kind of in this area here. But there, of course, also are versions of the prox Newton that fall into the quasi-Newton space as well. So you can do all of this same stuff using an approximation to the Hessian for H in place of the true Hessian. This can have some advantages. For example, if the Hessian has, if your approximate version of the Hessian has certain structured form, say it's block sparse, or if it's low rank or things like this that we know there is form, then actually sometimes the proximal map itself becomes much easier to solve. So not only do you get the added benefit of the not having to compute the Hessian, the true Hessian in the first place, sometimes you actually can make your proximal map also easier to solve. There's some work, for example, in using block diagonal Hessians that keeps things, only small Hessians are needed, so you can solve those prox maps much more efficiently, and all this kind of stuff. There's a huge range of optimizations optimizations of the optimization process that you can use here. And it's also, when it's actually, it's also be helpful when it's ill conditioned. So if your Hessian is really close to being singular, actually these things can help, even though they are, they can actually make it do better sometimes than the normal prox Newton. Okay, any questions there until I move on to the next and last thing? Okay, so the last thing I want to say, and actually I want to spend some time on this because it's something that everyone tries, including myself, and I was learning all this stuff. And the thing you try, okay, so let me show you the thing you try first. So everyone tries this. You learn about projected gradient descent in this course, and you learn about Newton's method. And so projected gradient descent, you take a gradient step and you project onto an allowable set. So if you have a good projection operator, a fast projection operator, you can do this efficiently. So the natural thing to say is, well, okay, I can also do take a Newton step. Those are better, and I'll just project that. And you will implement this probably, and you'll try it and see if it works. And lo and behold, it doesn't work. It doesn't do anything, in fact. You can see actually it won't do anything just by the fact that, like, for example, if I want to minimize a quadratic subject to some constraint that I can easily project onto, you can't just take the solution of the quadratic, which is what the Newton step gives you, and project that onto your set. That doesn't work. And so, of course, a projected Newton method would not work as you would hope it would work. But why is this the case? Because we've done prox Newton, that works. So why can't you just take a Newton step, then project onto your feasible set and hope everything works? And the reason actually falls out pretty nicely from just analyzing the proximal Newton method. So remember, when you would apply proximal Newton methods or proximal methods in general to the case where the function that you're applying the prox to, the non-smooth function, is an indicator set, then the proximal gradient reduces just to projected gradient. But trying to do the same thing with proximal Newton does not give you the sort of naive projected Newton method. So let's just see that for a second. Remember, I guess I'll just do so proximal gradient slash projected gradient. So if my function h here, in all cases, is the indicator of being in some set C of x, then our prox map here, right, our prox function is equal to the argmin over z of x minus z plus h of x, which is equivalent to the argmin. So this will be infinite if it's outside the set and otherwise 0. So this is just equivalent to saying we're going to minimize the argmin in this set of x minus z. So in other words, the prox operator just becomes a projection operator onto our set here when we pick our function to be the indicator of that set. It's like a box on the side. So therefore, proximal gradient is just naturally results in the same projected gradient method that we saw even earlier. But let's think about proximal Newton. What this says is that, I guess I'll just write it like this. So what this says is that our increment is or our new step is the argmin over z in our set of the Newton prox, or the equivalent term in the prox Newton map, which equals the argmin over c of I'll just write the second one here, our gradient times z minus x plus half z minus x transpose h z minus x. And this, of course, is not a projection onto the set C. It's something else, right? It's the minimization of a quadratic subject to the constraint of being in that set, which is in itself a hard problem to solve typically, right? We haven't really gained anything from this. So in general, you cannot just take a Newton step, which would be this thing here, and then project the result, because you have to do the projection under this norm h, which is a hard problem in itself to solve. Okay, so that's sort of the problem with projected Newton, is it doesn't actually, the thing you would think would work when you say projected Newton, which is take a Newton step and then project, does not actually work. It is not a valid algorithm. It will not actually give you a solution to a convex problem. So if you then Google projected Newton in frustration because you can't figure out how to get it to work, you will find something called projected Newton. And what that is this algorithm applied to special cases where you actually can solve this thing efficiently. But even then, it's not easy to do. It's actually quite difficult. And it only applies to certain types of constraints C. So in particular, the one type of algorithm where you really can make projected Newton work pretty reliably is on bound constrained problems. So if my constraints are so if my problem is of the form, I want to minimize over x some function g of x subject to the constraints that I just have some simple bound constraints on x. This actually is the case where if you work it out, you can derive the equivalent of the proximal Newton step here for a constraint. So in other words, this constraint. And it ends up being actually solvable with this, then with what they call a projected Newton method. But it's not easy. Okay, it's not sort of the simple thing. So let me just say how this works now. Actually, I have plenty of time, so I can say this works with some some amount of time. So here's the idea. What we're going to use is what's called an active set method to solve this problem here. I'll write it again up here. So I want to minimize over x, g of x, subject to L less than or equal to x less than or equal to u. Okay, I want to solve that problem. What I'm going to do at each time is I'm going to define a set of variables that are called that are called binding variables, variables at bound, and then free variables. So the bound variables are those variables at my current value. They're already at their lower bound or upper bound, and importantly, moving them. And probably the gradient points kind of away more into the bound itself. So they're both at the bound, and kind of the gradient of that function is pushing them more into the bound. So what that means is the bound variables at this time, k minus 1, equals a set of all I, such that, first of all, xi is, say, less than li plus epsilon. So epsilon is just some small number, and you actually just use some small number like 10 to the negative 8 or so when you implement this. So the gradient is, so the value is at the lower bound, and the gradient of this term, the ith element of the gradient, in other words, the thing that the direction we would want to go to make the thing smaller or the negative direction we want to go to make it smaller, of x k minus 1 is greater than 0. And I have to look these up to remember the directions as well that you want. But basically, if the gradient is greater than 0, that means a step in the negative gradient would push you further in toward the lower bound. And so not only are you at the lower bound, but you kind of want to go even more into that bound. If you're at the lower bound, but the gradient is negative, you actually will make progress by stepping away from that bound. So you don't want to fix that variable. You want to take a step in that variable. But if both you're at the lower bound and the gradient is positive, i.e. the negative gradient is pushing you into the bound, you want to fix that variable. You don't touch that variable. So obviously there's the equivalent thing for the other set. So this is going to be x is greater than or equal to ui minus epsilon, and the gradient of this guy is negative. So this is our bound set. This is a set that we don't want to actually touch. So we're only going to take a Newton step actually in the remaining variables, which are conveniently called the free set. So the free set of k minus 1 is just 1 to n minus the bound set. So it's everything else. Oops, that's a backward slash is set difference. Okay, so now what we're going to do is, and this is, by the way, all of this is that I'm defining here is essentially just a way of solving this inner prox operator when you have this particular case, but that's ends up being a projection. Basically, it ends up being a Newton step only in the variables that are not already at the bound. That's what the prox map ends up actually giving you. So what we do there then is we form this image is called S, which is the inverse Hessian of the Hessian only evaluated at those entries in the free set. So basically, I'm going to take a step in the variables in the free set, but I'm only going to take the Newton step, sort of like the intelligent step, in those free variables, right? So I'm only going to sort of look at be updating essentially the free variables. So that would correspond to the Hessian at this guy, k minus 1, only the set of them in the free set. And this whole thing I'm going to invert. This is going to take the rows and columns according to the free variables there. I guess Ryan just puts 1. Then I'm going to take a Newton step in the free variables and project everything back into the original space. So the way that we write this is that xk equals the projection onto L and U. That just means we take a step and then clip them back to the range L and U of xk minus 1 minus our step size, and we can solve this again with backtracking line search, times sk minus 1 and I. Not sure why it's this way, because these things won't go anywhere because they're already at bound and the gradient's pointing them in that way. So these, you could make this 0 too, but just for completeness, I guess, I'll make it this way. Times the gradients with respect to the free variables of, and the gradient with respect to the bound variables. So basically, I take a gradient step, or sorry, I take a Newton step with this sort of sub-matrix of the Hessian in my free variables, and then I project everything back into the set, and I restart. And by the way, these sets can change now, of course, right? Because two things can happen. A variable can be at bound before, and once I move the other variables, then all of a sudden the gradient points in the other direction, so it will no longer be in the bound in the binding set. And similarly, of course, I can have a variable that's originally in the free set that hits a bound, and the gradient stays in that direction, so then it actually enters the bound set. And the update, I mean, despite the fact that we have this I here, this is not touching the bound variables because they cannot move there. That'll always just, maybe take a step, but then be projected right back into the set immediately. Okay, so that's the projected Newton method. And this actually works incredibly well. It is, so I guess, yeah, so it's a paper that always will come up is if you read it is this Persikis 1982 paper. So when you, in frustration, Google projected Newton because you want to just take a Newton step and project, you'll find this paper, and it will look really complicated because it's doing this crazy thing about free variables, and you have no idea what's going on, but now hopefully you will. The paper also proves superlinear convergence, but this method actually has gotten quite a bit of traction in recent years, both because it's been used with quasi-Newton methods as well. So people have extended this, of course, like everything else we do, to quasi-Newton methods. But also, it turns out that really a lot of problems that we care about do have box constraints, and just box constraints, right? So a lot of things like the non-negative least squares, like a lot of actual dual problems. So like the L1. L1 is not a box constraint problem, but its dual actually is a box constraint problem. And so you can actually solve the dual of that problem and then recover the primal solution from that. And that actually ends up being, in a lot of cases, some of the fastest methods we have for solving these things. So like for the fused lasso, and not the graphical lasso, but the fused lasso I know, I think still this is one of the fastest ways of solving the fused lasso. So solving the dual problem with a projected Newton method and extracting the primal from that is actually one of the fastest ways of solving the problem that we know of. So this is a really practical algorithm that has a lot of nice applications. Here's an example from one of these papers showing, I guess this is an original image. This isn't, yeah. So the original, I guess it's impressive you can do anything at all with these things. They're super bad quality images. But here's the original image. Here's a blurred image that you observe. And they recover this image here with denoising techniques. So I'm not sure if it's that impressive or not, but maybe it is. I mean, here's one's a little bit more impressive, maybe. This is an image. You see this is a blurred image. You probably can't even see the fact that there are two dots here. That's probably largely just due to the projection. I bet they're probably there somewhere in the image. This is the original. This is the blurred image. And this is with the image recovered with a projected quasi-Newton method. Projected quasi-Newton, we're using an LBFGS type update for an approximation to the Hessian. So you quickly start combining all these things together, and you can form lots of new acronyms. And so PQN, LBFGS is, you see a lot of these kind of things. Whereas if you just use a straight LBFGS thing, it doesn't work quite as well. So these things really are incredibly useful, and they can be some of the best performing algorithms that we have and the fastest things we have for a wide variety of problems. Okay, that actually I'm done 5 minutes early. So are there any questions? Not to put pressure on anyone, because then you're stopping everyone else from leaving. But if you have a question, you can come in. I'll be happy to chat.